Desk Ladyada.
Hey everybody, and welcome to my desk. I hope you guys are all staying warm. I know that there's a lot of cold snaps around the US. I don't know, maybe it's also cold in other countries. But at my desk, it's nice and toasty. We got the soldering iron on, the hot air gun. We're making all sorts of prototypes. Let's go to the overhead and check out some of the prototypes that I've been playing with. Okay, so first up, for our cutie pie boards, I love making BFFs. These are little boards that either plug onto the back or in this case, going to plug on top. So for example, one BFF that I got prototype for is the CAN BFF. I think I showed off the design last week, but now I've got it. And this goes like back to back, like so. Actually, I think it actually goes like this. I have to test this out. And it uses, it's a nice little compact package, which I think is cute. You just power it with USB. And the 5-volt USB is used for the CAN bus voltage. And then you've got ground, high, and low signal. This uses the MCP 625, which is basically an MCP 2515. It's like the most popular CAN bus controller chip with a transceiver built in. And I know that some people are like, but wait, the ESP series can do CAN bus natively and RP2040, you can bit bang it. Yeah, but like it's kind of like it's challenging and the API is different. And I feel like, it's only a couple bucks. Maybe just getting a CAN chip over SPI and like it's good to go. Might be easier because you need a transceiver anyways. And then there's some jumpers on the bottom if you want the interrupt, standby, or reset pin used. Okay, so that's one. And then I designed another one. Mr. Ladyada sent me this link. Somebody made a board that allowed DC power in for Cutie Pie or Shao board. And I was like, oh, that's a really good idea. And Erin was working on a project. She's, does projects for us that she needed to power an ESP32 Cutie Pie from 12 volts. And I was like, I don't really have, so you can wire up like a buck converter, And she's like, well, I want something simple. So I designed this board. And inside here is the NPM 3610. So maybe pop back to my computer real fast and I'll show off this chip. So we have some breakouts for this chip. The NPM 3610. The NPM 3610, it is cool. I saw this actually in Arduino boards to start. Like I think the Arduino, the Giga, I don't remember. One of their boards used the NPM 3610 and I was, or like a bunch of their like nano boards used it. And it's a really cute little chip. First off, it's not too expensive. It's only a couple bucks. It's in stock at DigiKey. So let's look it up real fast. NPM 3610. It's an adjustable buck converter up to like 20 volts input, 1 amp output, and it can be adjustable, but like it's great for like 3 to 5 volts, I think is what it can do. And yeah, it's like, basically $1.50, $1.25, whatever. And what's nice is that it's got the inductor built in. So you'll notice like, whoa, there's no like inductor or diode or transistor or whatever. Everything's internal. All you need is like 4 passives just to like set the voltage. So if you look at the overhead again, so I needed to go with this partially because, oh, can you go to the overhead? The I didn't really have much space because I wanted to have this DC jack and like I couldn't, I moved it to the very top of the board, but then, it's like I went out of space. And then I wanted a terminal block also. So you could choose whether you want a DC power input. So you've got like, DC plug or, a battery input. And then there's a diode protector because, you can wire this up backwards and maybe you have like a center negative for some reason. And then there's a buck converter, and then you can barely see 2 little 0402 resistors to set the voltage, and then a bunch of capacitors for capacitance. And then it gives you 5-volt out. So the only thing that's different is usually with these, I have them like back to back. But I didn't make this back to back, and the reason is because this has this these pins that come through, and I was worried that people would just solder it onto the back, and it would short because it'll touch the components on the bottom. You can see it's touching, and not good. You could like really damage your board. So this one, I decided, because the DC jack is so high, it's going to be. You can see here, it's a autofocus again. This is a top side style. So let's see, USB up. Yeah, USB this way. So it goes like this, and then I don't know if this is plugged in, but I think it is. And then you power it and then bing. And then it's running circuit Python, so you see the LED blinking, and now you've got it running off of anything up to 20 volts. I wish it did 24, but you know, I think enough people are willing to like deal with just 20-volt max. It's still a lot. It's a couple of, you can run off AA batteries or like AAAs or a couple lithium ions in parallel or a DC jack. And then if you want to run it off USB-C, you can use one of these USB-C. This is what I'm running, USB-C to DC cables. And then it's like, okay, you can have a USB-C. And, you know, if you plug into the DC, of course, the same voltage comes out here. So if you need 12 volts to drive something else, it's like you can kind of share it. So this design's done. And just one little change I made, if you go to the computer again, thank you, is I was like, oh, you know, chances if you're using DC, you want to like attach it. So I added these little like mounting wings that come out the side, and you see little holes here. You could break this off, but there's 4 mounting holes. And then you can put the cutie pie on top, and you've got like a little compact thing that you can even like attach onto like a design. And then of course, if you want more, you know, BFFs, you can always stack them, but this one would be on the bottom. So that design, I think, is pretty good. So the only change I made is to add these wings. I'm going to book them, and this is good to go. Okay, I have a couple minutes, so let's keep rolling. Next up, thinking of 12-volt power, another thing I designed is one issue I've got is this comes up a lot for me, more than you think. So you've got these like analog RGB LED strips. And that one is like this one, for example. So these LED strips have red, green, blue, or sometimes they're like only white. Like sometimes we have like a 12-volt neon, like these strips. And these are 9 to 12 volt DC. And the problem is you want to PWM them because you want to dim them or brighten them, or like, you know, you have multiple colors and you want to fade them in and out. But then you need a transistor, and you need like resistors, and you need like the DC input. It gets like kind of complicated if you want to control, especially the RGB ones. Like you can see here, like you have a metro and then you have these two transistors. It's like, it's a bit of wiring. So I wanted to make this easier. So this design here is it's a stemma board, so you have like a JST-SH connector coming in. It's like a little bit like this, you know, the BFF. So you have the cable coming in. And then it goes into this chip, which is, actually, let's go to the schematic. It goes into a WS2811, which sounds a lot like 2812, which is like NeoPixels. And in fact, these chips were the original, if we go to like the Flora V1, which is discontinued, the original NeoPixels from way, way, way back when, they had a chip on the back. This was before there's all-in-one NeoPixels. Like now there's like a little LED with 4 pins and like data in, data out powered, you're like good to go. But before that, in the old days, back when, before we had cell phones and Netflix, we had to put chips on the back, and then you'd have an RGB LED, and it's common anode, and you'd wire it up, and then you would still use the same protocol, but you had a double-sided. And then, you know, this is discontinued because now the version, of course, has the chip inside the LED. But the reason we want to have the version with the LED external is because then we put it through an inverter and into 3 N-channel FETs, and these are like 3 amp N-channel FETs, and you have a V in here, and then these can sync the 12-volt signal, lots of current, so you have big LED strips, lots of LEDs, 12 volts, you know, even 24 volts I think they can handle. And the VN is also regulated down to 5 volts here to power the WS2811. So basically what I'm making is something that looks like a single NeoPixel, but actually drives like an analog LED strip, or even just like one of those big 3-watt LED chips. So actually, I think we have like 3-watt NeoPixel LEDs. So if you look at like, yeah, like these, it's the same kind of idea, right? Except that they don't, I don't know what these extra transistors are, but they have a WS28 11 here, and then big LED, and then transistors should actually do the driving. I think they do the same thing where they invert twice. So what's cool about this is that, like, you know, if this works, like, all you do is give it, like, the signal can be 3 to 5 volt DC. You give it 12 volts or 9 volts VIN, and then, like, boom, here's a terminal block, and you can just, like, drive your analog LED strips, and this should ease my annoyance of every time I have to do a demo for these strips. I'm, like, constantly rewiring the same circuit. So that's coming soon. And we'll talk about on INPI why I chose this and the design of this, not INPI, the Great Search. Lastly, right before we switch over to the Great Search, we have one. It's not out yet. Don't ask. It's a secret. So like 2 years ago, we were doing a lot of floppy stuff, and I had to take a break from it because I couldn't get, there were so many parts I needed I couldn't get that I was just kind of like going a little nuts. I was like, okay, I'm going to use this like buck converter. Oh my God, I can't get it. And then it's like, oh, this E-fuse. Nope, that's not available. I can only get this other version. And like it got like so annoying, and the prices were nuts. So I designed, this is actually floppy disk sized, and this is just like a rough draft. This is going to change around a lot. But it's an RP 2040 with a micro SD card, an SDIO format, and a TFT. And then this is a 12 volt buck converter, so you could give it 12 volts and it'll give you 5 volts as well. Because getting a split supply for 5 and 12 is annoying. And then down here, either your standard 34 pin IDC floppy, I don't know if I have a floppy drive here, or a laptop floppy. And laptop floppies use FPC connectors. And then your lovable Molex that everyone knows, the chunky power supply. And then all the level shifting, weight protecting, and then current monitoring too. This is the current monitor to monitor the 5 and 12 volts to see how much current is being drawn. Also verify that the voltages are good, because I noticed that if the voltages dip too much, you actually get some pretty, like you get bad data out. It's actually quite sensitive. And then this is an E-fuse up here. So this chip, we'll look at it real fast. This schematic is a little bit of a mess. I gotta clean it up. This is the power supply. This is the monitor, the E-fuse. The TPS 259540, which maybe I'll talk about some other dates. This is pretty cool. You give it, the power input, and it will only enable between the valid voltages. So I can tell it like, hey, below 12 volts, or below 9 volts, I don't want you to turn on and let the power through. And if it gets above, turns out like 13 volts or so, clamp the power output. And then if it overheats, the red fault LED turns on. So this will make sure people don't accidentally plug in too high of a voltage or too low of a voltage. And they're like, oh, why isn't it working? And then this is that buck converter. And yeah, I don't know. It's coming together. This is just a first draft. You see I got a lot of space. So I put this cute bunny. Please design this adorable floppy bunny, floppy eared bunny on some floppy disks. Very cute. So it's not out yet. Don't ask. I'm not talking about it. Maybe after a couple drafts, I'll get this going. And we'll do some more floppy projects. Okay, cool. We're ready to do the Great Search.
Where in the world is that part I need? The Great Search with DigiKey.
The Great Search brought to you by DigiKey, and for every single week, Ladyada uses the power of engineering to help you actually find the things you want on digikey.com. Ladyada, what is the Great Search this week?
Okay. Great Search this week is we're going to look for a triple inverter, and it has to be really, really small. So let's go to the computer and I'll show off the design that I'm working on. So here is a board I'm designing that will take a NeoPixel signal, WS2811, 2812, and convert it to analog LED strips. And the WS2811, if you look at the data sheet, it can handle high voltages, but it doesn't do high current. It only do like 20 milliamps per string, but I want to do much more than 20 milliamps because there's many in parallel. And so I need a transistor output. I need like strong driving transistors. The problem is, if you look at this, this is a common anode output, which means the LED is on when the signal is low. But if I have N-channel FETs, like I do here, a low signal would be off, not on. So I actually have to invert the signal before I feed it into these power transistors. So first off, because it's common anode, I think it's open drain. Actually, I don't know, but I'm assuming it's open drain. I have a couple little pull-ups here, just 4.7K. And then I need an inverter. And this inverter, I want it to, it can't be open drain. It has to be push-pull. So, Schmidt trigger output. It needs to be 3 channels, because red, green, blue. It should be able to run off of 5 volts, because that's the signal level. And it should be small, because it needs to fit on this board. And it has to be like really tiny, but I don't like BGAs. So like small, but maybe not too small, like just right, medium. So let's go to DigiKey and let's see what we can find. So first thing we look for is we just type in inverter. I mean, here's the, I could actually use transistors to do the inversion, but again, I want it to be very small and I want it to be push-pull. So let's look. So gates and inverters, 13,000 options, but we'll pare it down. Don't forget, there's dark mode, but I'm not going to have it on. Okay, so let's also only look for active. Let's just start with active and normally stocking. Okay, and then I want it to be an inverter gate, also known as a NOT gate. I don't want any other gates because I don't want multiple inputs. I want one in and one out, and it just is, the opposite. Okay, so let's select that. Okay, now we're down to 1500. Number of circuits, 3. If that's option, sometimes you can't get the number you want. So you're like, you want 4, 4 doesn't exist. You get 6, it's like 1, 2, 3. Like the ones are very cute, the little SOT 23s or whatever. You get 3, and then it goes up to 6 or 9. Okay, cool, no problem. Apply. Okay, now we're really down to only 140 options, which is nice. We're comparing this down. Next, we talked about open drain versus Schmidt trigger. So the reason I want it not to be open drain is because I want this to be able to pull the gate of these transistors high. It has to pull them high, and I want to do it nice and strong, nice and fast. Why have pull-up resistors if I don't need them? Sometimes you want open drain. Not this time. We're going to go with Schmidt trigger output. And then voltage supply. Remember I said this has to be powered from 5 volts because the input is coming from the WS2811 and my only power supply is 5 volts. So we're going to not select these 3.6s. And yeah, this one's fine too. 4.5, but the voltage might be a little lower. Okay, good. And now we want it to be small, but not too small. So let's see what's available because now I've actually kind of pared it down to about 100 options. Okay, so I don't want BGA, definitely. So let's just select everything but that because I'm not doing BGAs. Okay, I only got rid of 2. Okay, so good. There's actually quite a lot of options. Another thing is, okay, I'll be honest. There's 74 logic, and there is TC7 logic. I don't really know the TC7 logic. I do know one thing about so T logic is transistor level output, so it can shift down, but actually I don't really need that. I think I'll just go with whatever is available that is kind of like the low cost and around. So let's look at by price. Let's see what's around. To be honest, almost all these are good. Oh, there's some marketplace options, which are okay, but let's go with just to make it easy so I can only buy whatever, because marketplace is just a duplicate of whatever we already have in stock at DigiKey. Let's exclude that. Okay. So there's these Exons and there are some MSOPs. These are good. I'm a little biased against the TC7 series just because I'm not familiar with it. So I'm going to select only the 74 series because I know 74. Although I'll be honest, I'm sure the TC7s are equivalent. Okay, now we're talking. Okay, we got a lot of Exons, VSOPs, 74 HCs. Let's look at what's most in stock. That's another good way of telling, what's the most popular. This one looks not too bad. Basically anything that is 74 LVC inverter. This I don't know why. You know what? I'm going to select logic type. Sorry, features. I'm going to not sub the X. I'm going to have just Schmidt trigger because I don't know why. Had I think open drain once. Okay, here we're talking HC series, LVC series. The difference between the two is basically like voltage, quiescent current, and logic level high. And then is there voltage supply? Both are basically the same. Current output high. You know, I actually want the higher current one. I'm gonna go with the LVC because I want to be able to like really turn these on very quickly. I don't think it's gonna make a big difference, but if they're all about the same, something that can slew a lot of current for me, good to turn on these transistors. So I'm gonna go with this one, the SN74 LVC 3 gate 14 inverter. And there's lots in stock. And they're like 30 cents a piece. So this is my pick.
And that's a great search.
Where in the world is that part I need? The great search with DigiKey.
All right, that's our show
Okay.
for the week this week. Thank you so much for joining us on Desk of Ladyada. We'll see everybody throughout the week. Keep an eye on our blog, socials, and more every place that you can see us. Lots of surprises, lots of new products. We will see everybody next week.
Bye, everybody. Have a great week.